Hi everyone, this is the Center Development Team for the Fall 2020 semester. My name's Peyton.
My name's Sanjana.
My name's Kaylee.
My name's Winnie.
Okay, so the main purpose of the Center Development Team is to create low-cost sensors that can be used by plant operators easily and efficiently, and also have easy to manufacture and repair parts if anything happens to these devices on site. And the main purpose of these devices is to gain insight on the quality and efficiency of the water treatment process as it goes through the Eau Claire treatment plant. So the main two projects that sensor development has been working on this semester is a dissolved organic sensor, which is currently in its prototyping phase, and a Sludge Judge sampler, which is in its research and design phase. The dissolved organic sensor, uh, its main purpose was to uh, determine the amount of dissolved organics within the water along the Eau Claire treatment plant process, and to determine pretty much the efficiency and the amount of dosing of chemicals that needs to go into the water at each stage. And the main purpose of the sludge sampler is for plant operators to be able to determine the amount of different layers of organics at different processes or different stages in the process of the all clear treatment process as well.
Adding on to what Peyton said, our first project being the dissolved organic sensor, we kind of created this device in order to substitute what's on the market currently, which are turbidimeters. And we're doing this because turbidimeters can be quite costly. So this is just a more affordable alternative. And another reason being that turbidimeters do not always detect dissolved organics. So this again would be a more accurate device. So here's like a pictorial depiction of our experiment for the dissolved organics. So looking on the right side, we have a light source being shown onto a water sample or a fluid sample, and we have two sensors, both 90 degrees from the light source and directly across the light source. So this water sample we kind of created as different vials of water with varied concentrations of clay. And the clay is kind of our substitute for dissolved organics. So we would essentially be hitting light onto that sample and having two sensors read the light that's being scattered and transmitted. The light scattered would directly correlate to the concentration of the dissolved organics within the sample. And that is kind of what turbidimeters do, but by adding a sensor directly across, we have like a more accurate reading of the concentration. And then to the left, we have this 3D model of our sample cell box that we created on Onshape. So this sample cell box is kind of where we would be holding the water sample in a cylindrical vial, which you could kind of see in this opening. And we actually have two different sample cell boxes for two different sensors that we are going to be doing testing on, both an IR sensor and an RGB sensor. And the main difference between those two sensors is the light source used. So for an IR sensor, it would be a LED like laser versus a RGB sensor would be a blue light. And you could kind of see the difference within the sample cell box based on this inlet on the very right side of it. So this is perfectly shaped for an RGB sensor, which is like a cube shape, versus the sample cell box for an IR sensor is cylindrical. So this is just the circuit diagram to connect the sensors to someone's computer in order to measure the transmitted and scattered light. And we have code that correlates with it that you could find on our GitHub. So this is just a more step-by-step procedure of our experiment. To the right, you could kind of see the circuit diagram with our Arduino board, and we have it being connected to our sample cell box on the very right, with the circuits correlating to the light source and the two sensors. So within our experiment, what we did was shake up the vial, which had the dissolved clay and place it into the box and immediately run the code. And this is because we don't want the clay to settle to the bottom. That would give us inaccurate measurements. And we ran this code with 10 iterations because any less would be an unstable sensor and any more would read the settled clay, which is not what we want. And from there, we plan on taking 10 different values for each sample concentration and taking the average to reduce uncertainty.
Going off of that, we have just 2 more pictures of our testing apparatus. As you can see, it shows the casing and our Arduino board. And then also, as you can see, there's masking tape around the casing, which is just like indicative of kind of the issues we were having with keeping the sensors and the connections together and in the casing. Moving on to our testing, we ran tests with 3 different samples of kaolin clay and water and 1 without any sample. As you can see, the average scatter light values were all consistent around like 800 in intensity, and transmitted light was around 20. This is very interesting because they were all around the expected value for the 1,000 milligram per liter sample, which should have a lot of scattered light because the clay would deflect the light at a 90-degree angle. However, the 0 milligram per liter, or basically just water sample and no sample at all, should have a very high transmitted light value and a low scattered light value because there's nothing to deflect the light. Therefore, we kind of concluded that there's issues with our sensor and laser and just our setup in general. So we needed to do more tests to see what really the issue with our setup is. So we ran 3 more tests where we removed one of the components for each test. So as you can see, we did a test with no laser, 1 with no scattered light sensor, and 1 with no transmitted light sensor. The average scattered light and transmitted light values were all very consistent. Scattered light around 830, 840, and transmitted light around 14 to 15. This is interesting because we use the 0 milligram per liter sample, so the transmitted light should be high and scattered light should be low. From this, you can kind of see that it's pretty inconclusive whether there was an issue with our laser or our sensors, and that we need to do more tests to see if there's something wrong with our circuit or our setup, and just really figure out why we're getting these inconsistent and unrealistic results. Moving past what we did with the sensor this semester, we also worked on a sludge judge, which is used to determine the sludge blanket height in the flock hopper, to make it more efficient for plant operators to empty it throughout the day and just see how much of a buildup of flock there is in this tank.
So the picture you see right now is a picture of a commercial sludge judge. So a sludge judge is a tool made out of connecting pieces of high impact plastic that trap fluid with sludge and has markings on the pipe to determine how much sludge there is. The way that you trap the fluid in the pipe can vary from different types of check valves to different endings. And our goal this semester was to determine which one is best for our own needs. So the first thing we did was research different types of check valves. A check valve or a non-return valve is a valve that only allows fluids to flow through in one direction. On the left, you can see a picture of a ball check valve, which is very common and can be made for very cheap. A free-floating ball is used to allow and block the flow of fluids. In the middle is a diagram of a diaphragm check valve, which uses a flexible rubber diagram and differential pressure to allow and block the flow of fluids. On the right is a swing or tilting disc check, which blocks and allows the flow of fluids using a swinging disc on a hinge. The general advantages of these check valves are that you don't need any manual like tugs or pulls to close these check valves. The downside would be that it's a little bit complicated, can be very hard to replace once they break. After that, we researched on different types of endings that aren't just check valves. A very common method used in commercial sludge judge units is a floating plug. It consists of a handle, string, and a floating plug. Once the desired sample is collected, the operator can pull on the string using the handle and bring the floating plug up to stop the flow of fluid. Over time, the string may become weak or snap, requiring replacement, which is very simple. On the right is a picture of a rubber floating plug, which is another simple method that can be used to allow and block the flow of fluids. It consists of a rubber cone at the end of a straight wire or a plastic stick. Once the desired sample is collected, the operator pulls on the wire or stick, causing the cone to fold over the opening at the bottom of the device. This method might not be ideal because the user would need to be careful of the cone folding over prematurely. So what you see right now is a AutoCAD of our design at its beginning phase. So it features a long clear tube with multiple sections to accommodate for various aquaculture plant sizes and a string with floating plug at the end in order to collect the fluid. There's also a hook at the top in order to hold the string in its plugged position as it's hoisted from the fluids for operator use.
Okay, some of the future tasks that we plan to take on in these future semesters are specifically for the dissolved organic sensor is determining the reliability of the sensor. So as you can tell from this presentation, there was a lot of uncertainty when collecting data from our sensor, and we just need to figure out whether that's from the Arduino board, our code for Arduino, where there's some inconsistencies in there, or if it's the actual laser or sensor that we're using, which is causing this fluctuation in data, or actually consistency in data, which shouldn't be happening for the different variables that we're changing. Also, future tasks for the dissolved organic sensor is just testing more concentrations of Calvin clay in water, just to get a better idea of how it will react to these different scenarios and different concentrations of contaminated water, and then comparing those results to market turbidimeters to make sure that we're getting the right levels of intensity and absorptivity from these waters so that they're accurate. Another future task is we want to improve on the actual design of the sensor casing. We think some of the uncertainty could be coming from the actual color or material that the casing is made of. So we want to improve on the color. Maybe a darker color would be better because reflectivity is higher. So there will be less noise when calculating the intensity of light going through the water samples. For the Sludge Judge, we just want to conduct additional research. We're currently in the research and the design phase, so conducting more research so that we can make this an easy to use product for AutoCAD operators is what we're meant to do. So that's a future task that we want to take up. And then improving on the just actual design of the Sludge Judge so that it's flexible for different AutoCAD water treatment plants, and then focusing on the end nozzle in specific, which just makes it pretty much easier to use and a better tool for extracting data from the water treatment plant. Here is just an appendix showing different equations that will be used in the future to determine the absorptivity specifically for the dissolved organic sensor, and that can be looked at in our GitHub. Thank you. All our contact information is down below if you want to ask us any questions about the presentation, and thank you.